Yep.
Okay. Well, Enrique already told you the list of the cast of characters involved with this for the regional MOM6. And I'm going to talk about some of the nitty-gritty details of how to create new domains. And for me, the best tool for that is shown here. It's a global beach ball showing the land-ocean boundary. So you can just rotate the thing and figure out what orientation you want your grid to lie at and so forth for some domain. These models want orthogonal grids in some coordinate system, whether that's purely rectangular or possibly curvilinear. It's up to you. For me, I've been building these things in a flat coordinate system using a conformal map projection. Conformal means angle preserving. So what is a right angle on your flat projected space is also a right angle back on the sphere. So that maintains the orthogonal coordinate system. And Mercator is the favored map projection for equatorial domains. Lambert conformal conic is good for mid-latitudes. And of course, polar stereographic is what you need to do at the poles, where the other map projections kind of go funny at the pole. And some options for building grids. Pavel Sakov wrote an orthogonal grid generation code in C. And there's a Python wrapper that was initiated by Rob Hetland. But the latest version of this is at this address. People have for years used a MATLAB code called CGrid, and that has been discontinued. Support for that got discontinued, but there's a guy down in Australia who has a grid builder tool that's available to download, and I think it's also available as a Windows executable file if you can't run MATLAB. But I can't run a Windows executable, so I've never run this thing. Liz Drinkard and Alistair are working on a new grid generation tool in Python. It's still in development, so it's something for the future. Something from the past is the Wharf Domain Wizard, but I hear it's still working. And it's a Java program that's got a GUI to allow you to build rectangular domains anywhere in the world. But it doesn't have a curvilinear grid solver, it's just rectangular. And then the stuff I use dates back over 30 years from John Wilkins' thesis work. And it's a collection of things. But yeah, it's dated, so we'd like something better than that. And some example domains. This is an example of a grid that we haven't run because the nature of these curvilinear grids is that you provide the boundary and then the grid gets filled in by your grid solver, and you have the ability to specify the grid spacing along two consecutive edges. So if I move the mouse here, so I chose that the outer boundary has uniform grid spacing along it, and then the southern boundary provides some higher resolution toward the coast, and then that choice propagates all the way to the far side. But you can see that if you try to follow the coastline, even roughly, you get convergences and divergences in your grid lines. And the model solution accuracy depends on this delta x, delta y, the grid spacing. And so it's going to degrade here in the bay and then get better at these capes. And your time step will be limited by your shortest grid spacing, wherever that happens to be. So it might be here, for instance. And this is an example of why we've mostly gone to more rectangular domains. So you don't have this strange bumpiness to accuracy and the time stepping and so forth. For the Arctic, I did choose to use a curvilinear grid, partly because we wanted higher resolution toward the Alaska coast. And we didn't want a mid-ocean boundary condition because the sea ice boundary condition problem is even worse than the ocean boundary condition problem. So we pushed the other boundary all the way over to Europe here at very coarse resolution. And again, I could control the grid spacing along, say, this edge to push the resolution toward Alaska. And this domain, we ran it as a coupled ice-ocean model with ROMs. And it was okay, but it turns out that this boundary condition here at Bering Strait was problematic in that we provided, we forced the flow through there based on a correlation between the moorings there and the winds. So even when we didn't have mooring data, we could say, all right, based on the winds, we know what that flow should be roughly, but that was not ideal. So the next iteration of the Arctic domain is shown here. So we've pushed that boundary.
Kate, at this point, we're not seeing your mouse, so you're going to have to describe in words where you are.
Oh, sorry. Okay. So we moved the boundary from the Bering Strait to the other side of the Aleutian Islands. And this domain has roughly twice as many grid points as the prior domain. And so the grid spacing doesn't get coarse quite as dramatically as it did in the prior grid. But again, we've run this for decades of the ROMS coupled ice-ocean model. And it does what it does, but we're hoping to use a better ice model for the next round of this. And so looking to MOM6 with either SICE or SIS2, depending on what works well first or in the long run. Probably use both, try both. Anyway, this is an example of where, again, you want to have all your corners to be right angles for a curvilinear grid, but mostly we're using purely rectangular grids these days, as Enrique was showing. Okay, here's another curvilinear grid that nobody actually ran on ever, but it's an example of a grid that you could build if you wanted to. And this is the waters around Southern Africa. And then back to the rectangular grids, this is a Northeast Pacific domain. We built the first Northeast Pacific roughly 20 years ago for a Globex project, where the focus was on the waters off coastal Oregon and off the Gulf of California, or Gulf of Alaska. And the idea was to run the same ecosystem model for both domains. And the original NEP grid had a boundary up through the middle of the Bering Sea, and that proved problematic. So we had to push that northern boundary further, well, actually further east, west. So that has also been run extensively in ROMs, and Ken Coyle still has some funded projects running both this and a nested Gulf of Alaska domain here. And for this grid, I picked this map projection as a conical map projection. And I did the math to say, okay, this is some defining line, and then the slope of that line should be 1 over minus slope of that line, and figure out where the corners of the grid had to be in this map projection space, some XY coordinate system. And then the next grid was the CCS grid that Enrique showed. And I got smart and decided the math was easier if you pick a rotation of the map projection such that your grid is lined in the purely Y direction, X and Y direction. And so a line through by the tip of Baja all the way up to here, the Olympic Peninsula, is straight Y direction. and you can go offshore, whatever distance you go offshore. And it's pretty clear now that we didn't go far enough offshore, but it is what it is. So we need a next generation grid that does better than that. And that is the new Northeast Pacific grid that Liz Drenkard will be working on, has started working on. But I started, so my Y direction goes from this coast here past this Alexander Archipelago, and then goes wherever it goes up there in the East Siberian Sea. And we can choose to go further offshore, but I wanted to at least get past the Aleutian Islands here. And then we'll see if this is far enough offshore, this distance with the eddies you get off California. And the last grid I'm going to show is the Bering Sea grid that was actually built by that WRF grid tool by Rob Cermak. And it's at 10-kilometer resolution, and it's pretty cheap to run. It's one of the cheapest IceOcean couple domains I have. I mean, beyond a square box. So I can run this pretty quickly. And for this, I have started in September with no ice at all. So that's a pretty simple initial condition for the ice model. And then you see over a year whether you grow ice sensibly or not. And if you melt it all back in the following summer. The Bering Sea tends to have first-year ice, but no multi-year ice. So once you've built your grid, you need the fields on it, and starting with bathymetry, you want to have the best bathymetry you can get your hands on. And many global products are derived from satellites and have pits and bumps, especially near the coast. At least they used to. I haven't looked that closely recently, but for the Northeast Pacific, the Bering and the Arctic domains, I've used the International Arctic Bathymetry database where it exists, Seth Danielson's Alaska database where it exists, and then SRTM 30 for the rest. For the latest NEP domain, I used the Sasha Shepetkin's tools to generate the first guess at the landmass. And it's using the coastline database to get a first whack at the problem. Although it tends to have lakes and so forth. So you need to go back as a second phase, which is the single connect program. And you tell it which of the bodies of water in your grid is the one you want to keep as your main ocean. So say in the middle of the Pacific somewhere, you pick an IJ on the grid, and then single connect will turn every other body of water into landmass. Once you have the first whack at the landmass, you might choose to edit it. We have a PyROMs package that has a landmass editing feature. And it's a GUI, and I'll show you some pictures of that in the following slides. And there's also a MATLAB version, which predates PyROMs, that's available from the MyROMs, the Rutgers site. So the most important thing to do is to avoid these little bays next to the open boundary. Because of the nature of the open boundary condition, the way it's trying to estimate values of the velocity, say through this cell wall here, and it's using values that are toward the ocean. I don't know, you call this upstream if you're going out. And so I would mask in these 3 points for a well-behaved boundary condition. I know for sure that in ROMs, if you have a landmass such as this can go unstable. The estimate of the velocity at the open boundary can go unstable. So that's my advice, is to just fill in all these 3 points next to the, oh, sorry, you can't see the mouse. But it's probably clear which 3 points I'm talking about. 3 grids that are currently water but should be land. And this is an example from the Northeast Pacific domain showing exactly that problem at the open boundary here on the east coast or eastern side of the domain. This tool is showing you all of the ROMS points, including one image point outside of the domain, outside of the computational domain. In the conversion from the ROMS grid to the MOM6 grid, that outermost line of grid points is going to get thrown away. So you've got one grid point right here that should be turned into land so that you avoid that boundary instability. And so I've shown that here after the landmask editing. Another thing you might want to edit after the fact is, for instance, the Sea of Okhotsk wanted to be water and originally, and I want that to be landmask. I don't want problems from the boundary condition over here in the Sea of Okhotsk, especially with sea ice problems. So I changed just a few grid points right at the straits between Kamchatka and then the neighboring islands. And then I reran that single connect program, telling it again that my ocean body that I want to keep as ocean is here in the Pacific side. And then that filled in the Sea of Okhotsk as land. And the third thing you might want to check is often these coastal barrier islands are problematic as to guessing which points are land and which points are water. And I've chosen just to fill all that in to make sure things are well behaved at the coast there. All models want the same fields roughly. They want the latitude and longitude of all the grid points. Also, you need the delta X, the delta Y fields, the angle with respect to north, and the landmass, and of course the bathymetry. So building the ROMS grid file has all of these fields in one file. ASCII and POP want the landmass separate, as does MOM6. But I have converters to go from WRF to ROMS and then from ROMS to whatever else I need. And one field that's problematic sometimes in this conversion is the angle field. So just make sure after you've made the MOM6 grid that angle field makes sense, especially crossing the date line. Once you've built your grid, you need open boundary condition files and initial condition files. And we have 2 different generations of Python tools, mostly done by Ralph Toussaint, some help from Matt Harrison. And so those are all available online. And it's also a work in progress. Ralph is still building the new version with using Xarray and all the new modern Python style. The forcing file is usually handled by whatever coupler you're using. MOMs interpolate from global atmospheric fields to the model grid. And then the runoff, I'm using Alistair's regrid runoff program. I have a wrapper, so I don't have to remember what all things it wants. But there's a regional domain option to it that is still, it's a recent development. but it allows you to not include the runoff from the whole rest of the world. By nature, this regrid runoff is greedy, and it wants to make sure you don't miss any of the runoff, but you don't want the Amazon runoff flowing into your North Atlantic. And then this, I think, comes from Andrew, is to clean up the file format of the regrid runoff. You need to do a modified program just to make sure that it's in the correct MOM6 format. And then the last thing you need are these ASCII input files for MOM6. There's a data table, a diag table, a MOM input, and an input.namelist. The data table tells you which files to use for the air pressure and so forth. For CESM, you don't need that line in your data table, but if you're using the JRA runoff in this style, then you still need at least this one line in the data table telling it what runoff file to use. And then the MOM input is the bulk of the OBC choices, happens here. We have a wiki page describing what your options are. It's subject to change. We're still discussing some naming or some file input conventions, because the tracer problem, if you have more than 2 tracers, you can easily run out of the length of some fixed line length. Some of these choices are a new line for each segment, and some apply to all the segments. And please let us know if something is unclear in the wiki here. One example is, say you have 2 boundary segments. You need to tell it where they are and what kind they are. In this example, I've got at I equals n being a code for the end of the domain, or the far eastern side of the domain in this case. I have a flather boundary condition. And then on the western side at I equals 0, I have a specified boundary condition, or simple. Order matters in that, in this case, both these segments are at the edges of the computational domain, but if you're in the interior somewhere, you need a convention for saying which side of that boundary is the inside and which side is the outside. And the convention is that you're going to go around the domain counterclockwise. So in this case, at the eastern side, you go from j equals 0 to n, so that the left-hand side of your segment, as you're moving along that line, is the ocean side, and then the other side is the outside the domain. So for the Bering Sea, I've got 4 segments. For the vorticity and strain, I want to have the computed vorticity is the option I'm using. So I first have to turn off the default free slip options. And then I want the 0 biharmonic option as well. Again, the Bering Sea domain has 4 open boundaries. And I have to specify, it doesn't matter which one is segment 1, but I have to go around and in this counterclockwise order along each segment. So I've got a segment for each of the 4 sides, and all of them are flather for the barotropic flow, and Orlansky and nudged for the baroclinic flows, both the normal velocity and the tangential velocity. So the nudging timescales need to be specified per segment, as shown here. So this is in days, 3 days for inflow and 360 days on outflow. Brush cutter mode equals true means that I used one of those Python tools shown above. Actually, Liz Drenkard built my boundary file for me. but the brush cutter mode means that the file contains information on the model supergrid. And so MOM6 on reading the open boundary information needs to know to subsample and only read the U points at the U values on U points. And ideally, we would rewrite the Python tools so they only provide the information that you actually need. And then we could obsolete this brush cutter mode. For each segment, I need to tell it which file to read and what the variable name is for each field that it's going to read. So there's a code. Here, the values in parentheses are the names of the fields in the file. And this is the line that, for many tracers, you would easily overrun the limit of the line length of the line that it's reading. There's open boundary tracer reservoirs, and here these are applying globally to all of the all the segments, and we still have experiments to run to figure out what kind of values makes the most sense here for the reservoir lengths, both incoming and outflowing. And here's some hourly sea surface height from the Bering Sea domain, showing that the model responds to storms that pass through this area. And then things get quiet. So as Enrique mentioned, there's future work to do, especially tides, and better tools using a modern Python style for both pre and post processing. I have an interest in the landfast ice parameterizations with a funded project on looking at that. And Bob Hallberg is helping me with some algorithmic stability issues in both the Bering and the Arctic domains. That's what I have. Any questions?
Thanks, Kate. Questions for Kate?
I had a quick question, Frank.
Go ahead.
Kate, do you have to worry about your bottom topography in the sense that you have to massage it so that you have to obey the hydrostatic consistency conditions, and that will determine your vertical resolution given a horizontal resolution?
I haven't been worried about that. But I've got some instabilities in the Bering Sea domain, so that look like they're happening near the Aleutians. So we're still figuring that out, I'd say.
Okay, Alistair had a question.
Yeah, hi, thanks, Kate. I was curious about you did a lot of put a lot of effort into editing the landmask, and then it was occurred to me that the gradient of topography is a related problem on the boundary. I remember at MIT we had this problem where we had to actually make sure the topography was flat leading up to the open boundary. Do you make any edits to the topography other than the landmask?
No, I haven't generally done that. In ROMs, we'd have to smooth all of bathymetry, but never around the edge, especially.
May I chime in here for a sec? Sometimes you want to make sure that it's the same as whatever you have. It doesn't necessarily have to be flat, but you want it to be the same as what's on the outside so that the transport, I mean, if you care that the transport, the barotropic transport is the same, then the depth has to be the same. So if that's a consideration, then you can do that. And we have done that before. I think all the CCS domains, we did that at some point.
Andrew, you want to speak up?
Yeah, thanks, Kate, for the for that and walking through it. I mean, my main question is, so you described a lot of the tools and kind of generally described the workflow, but is there a write-up for one of the domains specifically, like in terms of like if somebody wanted to set up that domain from scratch, here's the actual workflow that you step through, like line by line, command by command?
No, but there probably should be. I think I don't want to do that until I start using one of the Python tools.
Right. Yeah. Gotcha. All right. Thank you.
Andrew, I think we're getting a lot of feedback.
Oh, sorry.
Yeah. Okay. Other questions for Kate? I guess I have a sort of a broad question, Kate. You know, at a couple points in the talk, where you were saying, you know, you had tried a certain domain and decided to push a boundary because of problematic, the boundary being problematic, or you saw. So what sort of issues is there a general characterization of what sort of things go wrong? Are you seeing the model blow up, or you just don't like the look of the solution near the boundary, or what is it that makes you decide a boundary isn't working right?
Well, in the two cases I mentioned, it was feedback from others. Like Seth Danielson was looking at my Arctic results, comparing to moorings that he's had in the Chukchi and Beaufort seas. And it's just a thought that having that boundary being imposed was too stiff, and it was just affecting the solution. And we'd taken away some kind of degree of freedom. And in the Bering Sea, I don't recall whether moving the boundary was due to interest in having a Bering Sea domain, because some of their cruises are there, and some of the, well, later there were projects in the Bering Sea, or I just don't remember.
Okay. Mehmet, you had a question?
Yeah. Hi, Kate. In one of your slides, there was this use biharmonic and vorticity true and false. I'm aware of the all these Orlanskis and whatnot, but can you comment on those options? What are those options are, and when do you turn it on or off in terms of the open boundaries?
Yeah, the biharmonic at the boundary, I don't know that there's a viable alternative to having that be true. So
and there is vorticity, right?
If you have a biharmonic viscosity, you need a boundary condition on, I think, the Laplacian, or maybe the gradient of the Laplacian at the boundary. And so we just say that that has a zero gradient.
Okay.
But yeah, I don't know if it's not true what that would be.
Okay, Bob, you want to make a clarification?
Yeah, thank you. So Gokhan asked about hydrostatic consistency. We have never worried about hydrostatic consistency in the in domains that don't have open boundary conditions, and never found any particular need to. Kate mentioned that there's some interesting issues with the stability of the algorithm. And this appears to be related to time stepping, not algorithmic, not hydrostatic consistency, in that we're able to shorten the baroclinic dynamics time step. And in Kate doesn't even know all the latest on this. We've been working on this very actively. But the shortening the time step, things go right through. Although there are interesting features that appear. There's a very deep trench right off of Kamchatka in her Bering Sea domain, and so having perhaps data extrapolation down to 7,000 meters is perhaps an interesting challenge. What we suspect is going on is that the open boundary conditions and/or storms may be triggering waves that are coming in, basically triggering something akin to tsunamis. So the velocities or flows are rapidly changing and can have significant amplitudes that are then interacting with the way the baroclinic barotropic splitting is occurring. And so we're looking at going back and redoing that problem even more carefully than we had before. But it's a particular challenge because the barotropic-baroclinic splitting is precisely where we have this Flather open boundary condition that's working so well in other cases. So there are some interesting intersections between the underlying algorithm and the open boundary conditions. And in some ways, the fact that we're kind of pushing the model into new and interesting and challenging regimes without trying to smooth to get past some of these problems is ultimately, I think, going to lead things to be much better. Kate is really good at taking a model and kind of pushing it for all it's worth and coming back and saying, okay, here's some things to look at. And so I take my hat off to her for being a particularly effective user at identifying anything that isn't quite up to scratch.